The list is a very important data structure in programming because lists allow us to create flexible data structures. So the concept of a list is that linked list, if we can call this a linked list, because there are links between nodes. So you allocate memory for a node, you put your data in the data field, and then you have a next field that will point to the next element address. So that's an address of another list node. And so we can create this kind of connection between these list nodes, and then final dummy node will go into the null. So this is the idea of a linked list. So the idea of a linked list is appealing because it is dynamic, unlike arrays which are static. That means we can allocate and deallocate memory as needed. And inserts and deletes can be done in big O of 1, unlike in arrays, where you have to ship things to fix things when you insert something. So here, assuming that we know where to insert or where to delete, we'll be able to do this in big O of 1. And then the third reason that you want to use a linked list is that there's no need for contiguous space. There's no need for contiguous space, unlike an array. So because you may not have enough memory to give, if you ask for n bytes of memory, you may not have that in one place. So you may not get it. Alloc can return a pointer, or alloc array can return a pointer, which is null, and so you will have to, you will not be able to come up with a good, efficient solution. So understanding linked lists allows us to create some very good solutions to some problems where we can manage memory in a more flexible way. So in terms of operations, we will talk about some of the standard operations, such as if you take a list, assume that with this list has 2 nodes and a dummy node, and then we like to add a new node called 3. So ideally what you'd like to do is to create a new node, make that the dummy node, make this pointer go to null, and then put the new element 3 in here, and then make sure that this pointer goes to the new node that's just created. So that's a good technique. So if you can find what the current dummy node is by navigating through the list, we'll be able to make this connection, and we will write the code to show how to do it. And removing something from the list is also done first by navigating through the list and finding what to remove. Once you find what to remove, let's assume that you're trying to remove this node 2, and if you know the node before that, which is important, and you will be able to make that pointer go to the next one and remove the node, unless the priv happens to be the first node and you're trying to remove the first node, and that's going to be a special case. And in terms of looking for something in a list, you can iteratively traverse through the list and look for that. Now, one of the things that is important for you to understand is that lists cannot be accessed in a random way, unlike arrays. So arrays are random access because they are all in one place. So the list requires you to go through each element one by one using the next pointer. So lists are not random access, or cannot be accessed by an index. And hence, we cannot perform something like binary search on a list, even if the list is sorted. From an implementation point of view, we will start with by defining a list node structure, which is defined with a data field and a next field. So you are going to look at something like this, where you package your data, and then you package your next into one field. So if the data happens to be an integer, and the next happens to be a pointer, then what you are doing is you can allocate memory, enough memory necessary for a struct list node that would give you, say, 8 bytes, and then you can make it go to some pointer list L. So this means that L is a pointer to one of these list nodes. Now, you can obviously create another list node. Let's say that you want to create another one of these guys. So what you can do is you can say, well, let's create a new one called L1, which is also a list, by using the same alloc. And so the pointer here is L1. Now if you like to connect these two nodes, then what you like to do is you have to make sure that the L arrow next is assigned L1. So that's the way to connect the two nodes in a linked list. And we'll see some of these things as we write the code. Now, so the first operation that we want to do is to list new. List new means that I want to create a dummy node and then make this go to null. So let's start by saying this. Let's create a dummy node. List L is alloc struct list node. Let's allocate a dummy node, and then let's make sure that we will assert that L is not equal to null. Important, because it's possible that if the alloc fails, that means alloc fails to give you memory, L can be null. Alloc will return null, so L can be null. Hence, we won't be able to do something like L arrow next is equal to null. Notice L arrow next is the pointer that indicates the end of the list. And then at this point, we're going to be returning L. And so we can ensure that the result that we are returning is not equal to null. So it gives you a valid list. The list can be empty. That means you only have one dummy node of the size 0, but it is not null to begin with. So one of the important functions that we can use in writing contracts is to make sure that the list segments are valid segments. If you are given a start and end of a list segment, so let's assume that this is the start and this is the end, and you want to make sure that all the links are connected from start to the end. If you find that one of these links are going to null, then that's the time for us to say that it is not a segment. So the code you would write is something along these lines. What we will try to do is to move the start pointer towards the end pointer, and if the start pointer meets the end pointer at some point, then we know that list is a good one. And so we will write a piece of code like this. While the start is not null, because it's possible that start could be null at some point, and the start is not equal to the end pointer, and we will check to make sure that we'll just keep moving the start pointer. So we will just say start is assigned start arrow next. So now when you come out of this loop, there are two conditions. One is either start is null. So if you find out that the start was null, then we know that it is not a valid segment. We will return false. Otherwise, we will return true. Otherwise, we have start is equal to the end, then we're going to be returning true. So if segment is a good function to check whether the list start to list end is a valid list segment. Adding something to the list, we will write the code now to do this. So in this segment, I'm going to show you how we can write code to implement the list data structure. So list is essentially defined as a pointer to a list node. So we have a struct list node, which is a large data type. And struct list node is defined with two fields. One is the data field, which is an element that will be defined in an element.cnode file. And next is just a pointer to the one of the list nodes. And then we have implemented some functions to check to make sure that there's linking from start to the end and list is not broken. We also implemented the function called listNew, which will create the dummy node by allocating memory for the dummy node. Notice that the struct list node, we allocate enough memory for a struct list node, and we get a pointer from here. We assign that to L, And then we assert that the L is not null, because in some cases, if the compiler is not able to give you memory to use for this new node, it will return, the alloc will return null. So it's important that we do check whether L is null or not, so that we can do dereferencing L arrow next and make it go to null. And then we return that new node L. So the first function we're going to be writing is called the list add. So the list add means that we are adding to the end of the list. So when we're adding to the end of the list, let's start with some preconditions. This thing requires that the list to be a list to begin with. So this will make sure that it is not null. And also it requires that it ensures as a precondition, it ensures that it is still a list after we add things. And it also ensures that if you take the list length of the result, which is going to be exactly one more than the list length of the original one list that was given to us. So let's make sure that those post conditions are going to be met. We can add more post conditions as we need it, but for now let's go and write the code to do this. So the idea here is that you will have to go all the way to the end and find the last node. So how do we do that? We can do it with a while loop. We can say while L arrow next is not equal to null, because if L arrow next is null, then we do know that L must be pointing to the last node. So what we do is we are saying L is assigned L arrow next. So we are moving the pointer forward. Now, so at this point, when we come out of this loop, we know that L arrow next must be equal to null. So, in other words, L is pointing to the last node. So what we like to do is then we will take the data field of L and put the new element X into that data field. But the other one, that we have to allocate new memory for the dummy node now, because we are using the dummy node for the new node now. So in order to allocate memory, we will call, let's call this L1, is alloc struct list node. So that allocates memory. We make sure that L1 is not null. And if L1 is not null, then we do have L1 allocated. That's going to be our dummy node. Now the next thing we need to do is we need to make sure that L arrow next will go to L1, and we need to make sure that L1 arrow next would be null, because that's going to be the new dummy node. And then we return from this function. So let's take a look at this function to make sure everything is okay. First we find the dummy, the last node, by traversing it, and then we set the data of the last node to the X that we are trying to insert to the end. We create a new node called L1. We make sure that L1 has been allocated memory, and then we make sure that the old L arrow next will go to L1, because L1 will become the dummy node now, and L1 arrow would be next. L1 arrow next would be null. Now I can just return from this, because adding to a list, end of the list, is not going to change the original reference of the list. So this should be a sufficient code for us. Let's write the next function called the isin. So this is sort of like searching through a linked list to find something in there. So first of all, it requires that L is a list to begin with, and it requires that it ensures, the post condition would be that list has not been, is intact. So it's still a list, and the list size hasn't changed. You can check all of those things. And also, and we can make sure that if it returns true, so if the result is true, it must be then list is the X is in the element, so we can call it, well, we cannot call this recursively, so I'm going to leave it like that. So for now I'm going to say just that. This is a simple iterative process that I'm going to go through. So the idea would be that I'm going to navigate the list as long as L is not equal to null and L arrow data is not equal to X, and I'm just moving the pointer forward. L equals L arrow next. Now when you leave this code, there are two things possible. One of the things possible is that if L happens to be null, that means we did not find the element, so we're going to return false. Otherwise, it must be the case that L arrow data is equal to X, so we can else return true. So if you look at this code, it is our valid code, because if L is not null, only we look at L arrow data to make sure that with the short circuit evaluation, if this condition is false, only we're going to look at this, which is the case. Because if L is null, then we do not want the L arrow data to be accessed. So this gives us the simple function is in. Now let's talk about remove function. Now remove function is a bit more complicated. So remove means that you have to find the element and remove it. So let's talk about some of the preconditions. So this requires that it is a list. It also ensures that after you remove something, it is still a list. And it also ensures that the element cannot be in the list anymore if you successfully remove this. So what is the logic for removing the element? So here's what I'm going to suggest. So we start with two pointers. The one point is called previous, which I will initialize to the first node. And the other pointer is called the current, which I will also initialize to L, the first node. So initially current and previous are pointing to the same node, which is the first node. And then what I like to do is I'm going to navigate through the list while the current is not equal to null, and current arrow data is not equal to the element that you're looking for. And then I will try to do the following. I will try to save a copy of the current in previous. So that means I'm moving both pointers forward. And I will move current by 1 to the right. Alright, so if you look at this code, we make sure that current is not null before we can access current arrow data. And so when you come out of this loop, few things possible. Now, if current is equal to null, that means we never found this X to be deleted. So we must return false because we could not delete the element. Okay, and if current is not null, there are a few things possible. So it's possible that the current arrow data, then when you came out of this, current arrow data must be equal to X. Now it's also possible that if the data at the X is the first node, we didn't even move forward because current is the first node and current arrow data happens to be that first node X. So we can test that condition by looking at the priv and the current. So if priv and the current are the same, that means we haven't moved at all. What that means is that it must be the first node that we are trying to remove. So let's make some changes here. When you remove something, it's important that we return a list, because it's possible that the list has changed because we changed the first element of the list. So therefore, if current is null, then what that means is we just return the same list. We don't do anything. That means we didn't find it. We just return the same list that we have. Now if previous equals current, that means we have to delete the first node. So the first node is deleting means that L, the first node, now becomes L arrow next. So if you return the pointer to the second node, that would become our first node now. So if pre-equals current, we're going to return L arrow next. Now otherwise we have to make some connections. So otherwise what we're going to do is we're going to take priv arrow next. We will assign it to current arrow next. So this means we're going to be bypassing the current node and assigning priv arrow next. So we are bypassing the current and assigning the priv arrow next to the current arrow next. And by the garbage collector, the current node will be collected. So at the end, we did not change the header or the first node, so we return L again at the end. So this is sort of the list remove code that we can write to understand how to remove something from a list. So finally, in this list video, we're going to talk about an algorithm that will identify infinite loops in list. Now we have a code called isSegment, but the isSegment can only recognize when a pointer is pointing to null. But it doesn't recognize situations like this where 3 goes to 4, 4 goes to 5, 5 goes to 6, and 6 goes back to 3. So the idea is that we have to develop an algorithm that will recognize a situation like this, and you will never reach the end of a list, and this can create an infinite loop. So one of the algorithms that can be useful is that we have two pointers. One is going to let's call this T pointer. I'll call this tortoise. And then one is called the H pointer, which is the hare pointer. And we assume that the H always goes 2 nodes forward. So we have to make sure that it's going to allow to do that. So H goes 2 nodes forward, and then T always goes 1 node forward. So T would go 1 node at a time. So we do know that if you keep doing this inside a loop and T and H keep moving, and H moves twice as fast as T, and T moves only 1 node at a time, there are a few things that we can recognize. One is that if the list is a good list, that means if the list ends with a valid node null at the end, we do know that H will reach that node faster than T. Now there are a few special cases we have to consider. We have to make sure that in this case, if you're going to do H equals H arrow next, we have to make sure that you have at least 2 nodes in the list. So we do know that if the list is a good node, good valid list, then the H will reach the end of the list faster. If it's not a good list, that means H will reach here, and let's assume that this is how it's going to go. So first H will jump here, and T will go here. And then H jumps 2 things. So H will come here, and the T will go here. And H jumps twice. So H will go here, and at that time T will go here. So H again jump 2 nodes. So H will come here, and the T will come here. So at this point, the T and the H are the same. So you can guarantee if this is going to continue, at some point they have to meet. You can prove that mathematically that they must meet no matter what the size of the loop is. And hence we can write a piece of code that will make sure that we check for T equals H. If you happen to have T equals H at some point and none of them go into null, then we do know that this has an infinite loop. So finally, we will wrap up this list lecture looking at some complexity of list operations. So list new is an O1 operation. All we do is just few operations to just a couple of operations to create a new node. This segment goes through the segment, so I can assume that the segment worst case would be O of n. You're going from start to the end. List add would also require O of n operations because you have to find the end of the list. So in order to find the end of the list, you have to do O of n operations, then you would add element to the end of the list. List search would also require O of n, because in the worst case, it can be the last node in the list, or it may not exist at all in the list. And so you will go through the list looking for this node. List is sorted. If you're testing whether something is sorted, then you can do that in big O of n, same as looking for something, looking if an array is sorted. Now, sorting a list is really hard, because sorting a list would be, I would say that you can do that in n squared, because sorting a list would be more like something like this. You can take a list, let me draw a little picture here. Let's say you have a random list like this, 2, 1, and 3. So when you want to sort this list, you can create a new list called L1, and you take the first node and insert 2 to the, it becomes the list 1. Then when the 1 comes, you must insert 1 to the beginning of the list. So the 1 would be inserted here to L1, and then 2 comes here. The next time 3 comes, 3 goes to the end. So it's sort of like insert in order type. So you have to perform insert in order operations on the list. And as we know, to insert the first element, you only need 1 operation. To insert the second element, you may need up to 2 operations. To insert the nth element, you may need up to n-1 operations, which we know, as we have seen, it would require O of n squared. So the list sort is O of n squared. This remove can also be done in O of n. O of n is because you have to find it. That's why list remove is O of n. But if you do know the location, it can be done in O of 1. Okay, this means know which node to remove. Okay, so you have to find the node and remove. So we are making those assumptions in order to understand this complexity arguments. So we have listed here the complexities of these operations possible under certain cases. And so this sort of wrap up the complexity of part of the list operations. One of the interesting list applications is really what's called the gap buffer. So the gap buffer is essentially that if you have a text file, and if you're editing a text file, you can think of something like Notepad, where you have a cursor at a certain point and you like to insert a character at the cursor point. So how do we insert this in big O of 1? Because if you do this as an array, you have to shift everything to the right. So one of the ways you can implement a gap buffer is that we have a point where we can insert something before the point and make that the new point. And we know the start of the buffer and the end of the buffer. So what you have is sort of like a buffer that contains data fields A and B. And then this is sort of like a special linked list where you have each node has a data field and a next field and a previous field. And we'll talk about this in homework 4, how we implement a text editor using a linked list. So this wraps up the lecture on list.